or something. So our main topic today will be the gradient, and then if we're lucky we get to jump off to more stuff, but let's talk about the gradient. So I usually like to write the gradient with an extra line to denote that it's a bold face. This symbol is called nabla. Nabla, I don't know. And for some people, it might help if you throw an arrow on top, just so you can make sure that you understand that it is in fact a vector. And depending on how many input variables, how many independent variables you have, you'll look at this as a vector of 2 or 3 or 4 components. It's simply a vector of partial derivatives. And to be clear, it's the first order partial derivatives. Okay. Now there's a couple of important properties that you should relate to the gradient, and these properties can be extended to 3 or higher dimensions, not just 2 dimensions. But we'll take a look at the properties first, and then we'll take a look at the extensions, and then we'll do some examples. All right. So let's talk about how we first came up with this gradient, and then we'll talk about how the property will come about. So the gradient, how should we do this? And you understand when I write this, right? What does this mean? So the directional derivative of f in a direction of u. Okay? And we saw that this thing is equal to the gradient of f dotted with a u, provided that u is a unit vector. Yeah. Yeah, because that's all we need from you is just a direction. We don't need. Yeah. Yeah. All right. Now let's look at this where f is a function in x is a function of 2 variables in 2D. So for this, we can think about this as being equivalent to being on a mountain and you have a 2-dimensional map. And so you're kind of focused on the map in 2 dimensions. And let's fix ourselves to a point AB in the domain So if you're fixed at a point AB, what can you say about the gradient of AB? What can you say about that? I don't know if that's a... No. Just the first part of that. It's a vector. Now, since we have no idea what this function is, and I have no idea what this, I mean, if you have a function, f of x, y equals something, something with x's and y's in it, then you simply take the partial derivatives and you put a, b in. So at this point, we don't know much about it, but all I know is that there's going to be some vector, and then it would make most sense to put that vector from the point AB. Okay? So now, here's the thing. If we get ourselves a unit vector, that looks too thick. Can we thin it, thin it, thin it out? If we get ourselves a unit vector, then we can find a directional derivative if we go in that direction, right? So a curious question would be, which direction should we go which direction should we go to find the maximum rate of change? So imagine you're on the mountainside, and then there's certain directions that you can walk where you're going to have to go up the steepest, right? And there's other directions that you would walk where you would just, maybe you might go up, maybe you might go down. There's other directions you would walk where your height won't change at all. So this question is asking which way should you go to get the maximum rate of change. So to answer this question, we want to maximize the rate of change. So what is the rate of change? Well, the rate of change formula is something that I wrote up there already. So this is what we want to maximize. And then we could do this at a particular point AB. I don't know if that's going to mess people up, but that's just, let's just say it's at the point AB. So this is the gradient of f evaluated at AB dotted with u, the u vector. Now there's some important aspects of this that we need to consider, that at a particular point this is fixed. The gradient is fixed. It's constant. That's to say that after we put in the values of a and b into those partial derivatives in that vector, then you're going to get numbers, and that's going to say that that's your gradient at that point, period, and then that's it. And then it seems like we have choices for this. we have choices for u. We can make u go in many different directions. All right? So our plan is to move u around to see which is going to give us our maximum. All right? But, you know, there's an infinite number of directions to go, so how we're going to limit our choices. So what we're going to do is we're going to use a special property of the dot product. I don't know if it's special, but we've seen this before. What's the dot product equal to? It's equal to a lot of things, but name one. It's equal to the magnitude of each of these things times the cosine, right? Oh, my dot was a little too big there. This is times. And times the cosine of the angle between them. Okay? Now remember, we're flexible with u. We want to change u around so that we have the maximum possible value here. What can you tell me about the magnitude of the gradient evaluated at AB? Yeah, it's constant, right? The vector itself was constant. You take the magnitude, it's still going to be constant. It's just going to be a scalar now. So this thing cannot change. And we kind of already said that. We said this is fixed, it's constant. We're not going to be able to change the gradient because we've already took the derivatives, evaluated a specific point, so that's going to be fixed. What can you tell about the magnitude of u? What? Is 1, right? Because this is a unit vector. And then so we only have this left to manipulate. Now remember, we're manipulating the direction of u. In manipulating the direction of u, we're really just now looking at manipulating theta, the angle between them. So the question is, we want to maximize the rate of change, and we're left with this equation or expression. How do we maximize this? So we maximize this by just well, we can't change, this is fixed, right? We can't change the gradient or the magnitude of the gradient, so how we just left to maximize a cosine of theta. And when is the cosine of theta a maximum? Max at theta equal to 0. So, if the maximum happens when theta is equal to 0, what does that mean? It's going in the same direction as the gradient. Max happens when the unit vector is pointing in the same direction as the gradient. Now that fact, and we proved it, that fact is one of the biggest attributes, the biggest properties of the gradient, is that the gradient gives us the direction of maximum increase. We can also say a little bit more. What if we change the idea of maximizing to minimize? What can you say about the angle? What angle gives you the smallest value of cosine? Pi over 2 would give you 0. Pi would give you -1, even lower. But it's -1, which is going in the opposite direction. So the minimum value for this happens to be the complete opposite in sign, positive to negative, and then that would result in a decrease. If you think of a slope, it's decreasing if it's negative, so the maximum decrease points in the opposite direction. Of the gradient.
So really the vector u such that for the unit vector u such that the derivative at maximum it's just the directional derivative at that point unitized.
Yep, made into a unit vector.
And the minimum would be -1.
Yep, going in the opposite direction. Okay, so let's take these pieces of information. Actually, I have this theorem here, which we just kind of proved. Oh, we didn't quite finish it. It says the directional derivative. Oh, let's just take our argument a little bit farther. Actually, let's just copy this. So half of this statement is what we proved so far. And then the other half of the statement says that the directional derivative is actually equal to the magnitude of the gradient. Let's figure that out. Let's see. Find the directional derivative where u is in the direction of the gradient. So what we want to do is we want to make sure that we have a unit vector, and that would just be the gradient of f divided by the magnitude of the gradient of f. So according to the formula, du of f is equal to the gradient of f dotted with u, but what's u equal to? U is equal to the gradient of f divided by the magnitude of the gradient of f. And yeah, so this is equal to the gradient of f dotted with the gradient of f divided by the magnitude of the gradient of f, which is equal to the magnitude of the gradient of f squared divided by the magnitude of the gradient of f. And so now we're just dealing with constants. And now it's just the gradient of f magnitude. Okay? All right, let's see if we can do a problem. I didn't log into my account yet. Let's see if I have some problems in the book. One of these problems over here from '21, '22, 23. Let's do one of these. Which one should we do? Pick one. '23. All right. So let's go through the process of finding out the maximum rate of change and then the direction in which it occurs. So this is our function, sine xy, and then our point is at 1, 0. So let's figure out what that is. We need fx, the derivative of this with respect to x. The derivative of sine is cosine xy times the derivative of the inside, the derivative of xy with respect to x. And treating y as a constant, it's just going to be y. And then fy is going to be the same thing, except when you take the derivative of the inside, you'll get x. And so you want to plug in the values of 0, 1 in there. So fx evaluated at 0, 1, which says that x, oops, I'm sorry, that's 1, 0. 1, 0. So x is equal to 1 and y is equal to 0. So it looks like y is equal to 0. We'll just make this whole thing equal to 0. Fy of 1, 0. X is equal to 1. Cosine of 0 is 1. So that's just going to be 1. So the gradient of your function evaluated at 1, 0 is going to be the vector, and this is fx in the first component, and then this is fy in the second component. So it's just equal to 0, 1. So you can stop here and say this is a direction of maximum increase. Which means if you're standing on a mountain in the shape of sine xy and you're at the point 1, 0, then you would want to go the direction 0, 1. 0, 1 is like the going in the y direction, right? In the j direction. So you would want to go in the y direction or north to get the maximum increase. Now, to actually find the rate of change, all we have to do is find the magnitude of our gradient. We don't have to go through all that work anymore of finding directional derivatives and putting the directional derivative formula to use, because we know that the maximum increase is actually going to be the magnitude of the gradient. So the magnitude of the gradient at 1, 0 is going to be the magnitude of 0, 1, which is going to be the square root of 0 squared plus 1 squared, and that's just going to be equal to 1. The square root of 1 is equal to 1, so this is it. Say maximum rate of change. Which means if you're on this mountain, sine xy, and you're standing at the point 1, 0, if you go in any other direction, your rate of change will be less than 1. But if you go in this direction, 0, 1 direction, then that's going to be the highest, the steepest incline from where you're standing. And then the steepest decline from where you're standing would be the opposite of that, which is 0, -1. Okay? So the same idea works in 3 dimensions. We can quickly do this other example over here, number 24, since this is a 3-dimensional problem. Except this time you have 3 components. So we're looking at fx, fy, and fz. Let's see if I gave myself enough room for this. Nope, probably not. So your gradient will be a 3-dimensional vector. So the derivative with respect to x, oh, how do you do this? Just 1 plus y over z, maybe? Is that right? Yes, 1 over z. That's what I was just checking to see if you guys were right. 1 over z. So the best way to think about this is to split this up into 2 fractions, x over z and y over z. Maybe that'll be helpful. Fy will also be the same, I think, 1 over z. 0 plus 1, yeah. And fz, maybe it will fit. X plus y is a constant, and then you have 1 over z, derivative of 1 over z is negative 1 over z squared. So negative x plus y over z squared. So if we all agree that those are all correct, I hope they're correct, then we can move on. We have to put 1, 1, negative 1 in, so 1 in for x, 1 in for y, and negative 1 in for z. So we have fx. Let's just go ahead and jump to the gradient. So 1 in for z gives a negative 1 for the first component, a negative 1 for the second component, and 1 plus 1 is 2 divided by 1 with a negative. I think that's right. Is that right? Is it right? 1 over negative 1, right?
Yeah, put y instead of
Oh. Okay, so by the way, if that wasn't clear, leave a little space in your notes and then actually take derivatives carefully. Okay, so this is the direction of maximum increase, and to actually find the maximum increase itself, you take the magnitude. So this is just a square root of 1 plus 1 plus 4, 6. And I don't think you can simplify that. So here are the direction and this is the maximum increase itself. Direction of maximum increase. Okay? Any questions? All right. Let's go to the other very important property for the gradient, which you probably saw when I was copying my notes from my Word file. But I'm gonna prove it in a kind of weird way. Not a weird way. Weird. Maybe it's weird. I'm gonna see if I can use some graphs and some information that we've seen before to prove the next property for the gradient. And that property says that the gradients are perpendicular to level curves. So in order to do this, we need level curves. So I'm going to go back and draw pictures. So a picture that we've seen before, and possibly are sick of already. I told you it's my favorite surface. We got surface, and we have a point in the domain, and then we have this point on the surface. That would be A, comma, B, comma, f of A, B. But I'm more concerned about the level curve itself. So we have to imagine that we're going to cut this with a plane. And then we're looking at a level curve, but really we can look at that level curve flat on the two-dimensional plane. So let's get that view, AB or XY. So this is our beginning view of this scenario. So what we're going to do is we're going to take this curve, this level curve where we cut it with some z is equal to something plane. Z is equal to, let's call it C. Okay, so what we're going to do is we're going to parameterize this. And so what that means is that we're going to be able to find some parameterization, R of t, with an x and a y component as functions that would draw out that two-dimensional vector. Okay? And what we're going to do is we're going to take that curve and project it up onto the surface. What does that mean when you project the curve up onto the surface? You add in the z value. So what's the z value we're going to add in? What? Close, not quite. I'm looking at the curve r of t, and I want to project it up onto the surface, which is, what did you say? What did I say yes to? You give it a z parameter. So you have x of t, y of t, and then you project it up on the surface, and then it becomes, I don't know what to call it. Let's call it capital R of t, because I can't think of anything right now to project it. So I have x of t, y of t, and then now the third component is what I'm curious about. You give it a z component, but what is this z component going to be? Yes. Did you hear what Travis said? F of x of t, y of t. I actually want to rewrite that. Well, actually, let's write it as f, exactly how he said it. X of t, y of t, which is, we can call it g of t, but I was interested in calling this something else. What's x of t and y of t put together? What? R of t. Yeah, tiny r, little r. Okay. Now, so here's what we did. We took a surface, we cut it with a plane that happens to contain A and B. So we're kind of selective about that plane that we cut. We cut it with a plane Z is equal to C, and after making that cut, we came up with this curve that intersected that plane and that surface, and that's a level curve if we drop it down to the XY plane. So we drop it down to the XY plane and we take a look at it on the XY plane, and then we can parameterize anything. Some easier than others to actually come up with the equation, but we can parameterize anything we want, and so we'll call that little r of t. So by parameterizing this curve, we have little r of t. We didn't talk about this, but we can also say that when t is equal to 0, it's at AB. It actually doesn't matter where t is, but at some point we pass through the point AB. Now the next thing I was interested in doing, oh, this looks like a fraction. Next thing I was interested in doing was projecting that up onto the surface again. So I made up a new function, a three-dimensional curve this time, that has an x of t and a y of t, the same x of t and y of t that we had, but then we have a z of t that now we need to consider. And in projecting this is when this is one of our motivations for doing the chain rule, is that we say we put the r of t function into the f by projecting it up on the surface, and that's exactly what we're doing here. And now we have a composition of a function of two variables, f, and a function of one variable that gives out two variables, r. So now we have a composition. Now I kind of gave the next punchline is to take the derivative of it. But before we take the derivative of it, can you tell me a little bit more about this z of t that we just found? We projected this up onto the surface. Backtrack the story now. Think about what that projection onto the surface, where that came from, and then tell me about z of t. Tell me about that z. Evan said there's a z value. We need to have a z value for this. Tell me about that z value. So maybe instead of B calling it z of t, tell me about that z. That.
I'm a little hesitant to say it.
Say it.
It's that value is the z value is equivalent.
Say it.
The z value is equivalent to the z. If I'm imagining that if we're projecting it onto this from AB to some point on that z equals c plane there, that it would be perpendicular. That the z of that is perpendicular to the. I think.
No. That was close. It'll be equal to the plane. I thought that's where you were going. But yes, it'll be equal to the plane. What does that mean, it'll be equal to the plane? Constant. Yes. Constant. Do you see that? We can call it C, because that's the plane that we cut it with. We can also call it f of AB, because that's what happens when you plug AB in. You're going to get this height, a z value. But more importantly, this is constant. Does that make sense? Now, it seems like whenever we have something equal to a constant, we really, really want to take the derivative of it. That's what we're going to do. Yes?
What does that big R of t stand for again?
Big R of t is this circle up here in 3 dimensions.
Okay, so it's that little bowl.
Not the bowl shape. Maybe I should do this in green. R of t is this. It's a 3-dimensional curve. It's a curve that lives in 3 dimensions, right? That has the same x and y value as that level curve that we parameterize. Okay? This curve?
Yeah.
So that we can put it back into the function. So that would be more like a trick to this proof. This is, we're proving, we want to prove something, and then we're going to need a parameterization. So that's why we're doing it.
So it looks like once we prove this, we don't need to
Maybe.
don't let this happen.
Seems like we're drawing all these things out. But I'll say that you don't necessarily have to know it, but you know, these things might come up again, and I might ask for little details of things. I wouldn't say that you have to, no, maybe. I was going to say no, but I think I have given it as an exam question in the past. So I would consider this more of a candidate for a test question than like, you know, how I developed the tangent plane in a couple of days ago, where I found going in X, going in the Y, we cross it, and then that kind of stuff. So. All right, so let's take a look at what we're doing here. This is the equation that we came up with. And then from here, we're going to take the derivative. Now remember that this eventually is a function of just one variable, so we're looking at a straight d derivative, not a partial derivative. So we're going to say d dt of both sides of this, and remember the derivative of constant is 0. That's going to be on the other side. But what's going to happen on this side? So this now is a chain rule. And I don't know if you remember in the last lecture, but we've consolidated the chain rule into, you remember what happened? Into the gradient of f dotted with the derivative of r. It's like the derivative of the outside times the derivative of the inside. It's like the most natural chain rule that we've done compared to the other chain rule that we've done in the past. Except when you say times, it's a dot product. And then this is equal to 0. Yeah. Why, which works? Oh, okay. So if you remember back, we did some sort of tree, something like that. We got f as x and y, and these are all both functions of t. So then the derivative is going to be the partial of f with respect to x times x prime plus the partial of f with respect to y times y prime. And then we split them up.
So this, so the f flat tree there,
Yeah.
helps us see how it is parameterized. So it's like, say we have a function of 3 variables. If we're given a function of 2 variables and we're asked to do that, so we would have to go to x, y, and z.
Yeah. And then the t in the bottom, if it's just a function of one variable t.
And which is what we're doing.
Yeah. And so fx and fy can be grouped together as a vector, and then x prime and y prime can be grouped as a vector together, and so that's how these things came up. And whenever a dot product of two vectors are equal to 0, the dot product of two vectors is equal to 0. Is. That means they're perpendicular. This is a therefore symbol. Now r prime describes the direction of the curve, right? It's tangent to the curve. So r prime of t is some direction, maybe going this way, maybe going the other way, it doesn't really matter, but it's a vector that's tangent to the curve. And you're saying that the gradient is perpendicular. So then the gradient, I have two possible directions to go. The gradient's either going this way or going this way, as long as it's perpendicular. But then, that means it's perpendicular to a level curve. Not only that, little rt is a level curve, yeah. It's perpendicular to a tangent to a level curve, which in essence is saying it's perpendicular to a level curve. The gradient is perpendicular. No, this is 2 dimensions. So we're here.
Right. Surface in terms of the arc of
Well, it's the gradient is perpendicular to a tangent vector to the level curve. Therefore, it's perpendicular to the level curve. Yeah. Jonathan, you have your hand up?
I'm just thinking without as much of a formal backup, you could just say if you're on a level curve and you were walking with it, you wouldn't be making any rate of change. Rate of change is equal to 0.
Yeah.
Your cosine of that would be like the weird off ones of pi over 2s and 270 or whatever.
Yeah, 3 pi over 2.
Right? And so it's kind of, you wouldn't make no rate of change.
Right.
Get out with this definition now. I don't know if that helps.
Well, if it helps you, then that's great. So what Jonathan was saying is that if you go along, if you're on this mountain and you're standing on this spot right here, right above AB, and you're looking at your map, if you go towards the direction of the level curve, then your height is not going to increase or decrease. So that's what it's saying, or that's what he's saying. Yeah.
So wouldn't that be enough to prove the perpendicular?
Yeah, but I think what this particular proof is showing even more so is that how do you show that something's perpendicular to a level curve? Well, what we need to do is we need to find a tangent to a level curve, and if we can show that it's perpendicular to the tangent of a level curve, then we've shown it's tangent to the level curve itself. That it's perpendicular to the level curve itself. Okay. So it's perpendicular to a level curve. Oh, here. I drew two vectors. If you had no idea how the function looked like or how the graph looked like or what the function is, I would say it's one of those two vectors. But I have a picture of the graph. Which of these two vectors that I drew is the actual gradient vector? The real gradient vector. Please stand up. Been listening to Eminem. So. Which one of these two vectors, the one pointing in or out? Okay, the hint is to look at the mountain where you are and look at what we just proved before this.
So the gradient points in the positive?
The gradient points in the direction of maximum increase,
Inwards.
right? So if you're on that mountain and you're looking at the map, which way do you go to find the fastest increase? You go inward or outward? Inward. So your actual gradient goes inward because from the mountain, this is going to be the direction you go to feel the maximum increase. If you go the other way, you're decrease. So this is actually the negative of the gradient. Yeah.
If it's max increase, then it's towards the inwards.
Well, it depends on how your function is shaped. If this was a bowl, if this was the shape turned upside down, then your gradient is going to be pointing outward.
What about using like directional derivatives? Directional derivatives are all positive, or if they're mostly positive, then you're decreasing.
You could do that, but directional derivatives, you'd have to use that formula, and there'd be more work than you need to do, because now you know that the directional derivative, that the gradient gives you the maximum directional derivative. Positive, yeah. Okay? Yeah.
So what kind of approach would you recommend to solve a problem where, like, if, say we're asked to find whatever we did with all of this business, how would we define which of those is the correct one? Like,
I think what you would, in a visual problem like this, you would need to look at how the graph is shaped of the actual function. If you don't have that, if you have the functions themselves, then you might just have to find the gradient itself by taking derivatives, and then you can figure it out from there. So those are two of the approaches that I can think of. Should we try to squeeze in a problem, or just leave you responsible for figuring it out? You guys seem like you're packing. You're all set. You guys know what you're doing. So. It's all good. I don't know exactly what the homework problem looks like, but for this section, I don't know if you could tell, but I really, really like this section. You might want to actually look at the problems and then, work on the odd problems in the book and then check your answers to make sure that you're doing it correctly. You're going to be pretty much guaranteed one of these types of questions on the exam. It's a word problem that uses the idea of directional derivatives and gradients and the properties that we just proved today. And it could be in 2 dimensions, like in problem number 34, or 3 dimensions, like in problem number 31. So think about it, know it, and if you could just follow through the proof again, that could be helpful too. Okay, good luck.